Our next speaker, Mr. David Huberman, Regional Technical Engagement Manager for ICANN's Office of the CTO. And David has actually been within internet engineering industry since 1999. And I see he has worked for Microsoft, Global Crossing, Oracle, Telocity. And the fact is that the Retail recently ranked him as the second global influencer of CIOs. His topic today will be about DNS security and the Root DNSSEC KSK Ceremony. Well, it's a fun topic to start with. Let's welcome David Huberman. Please, a nice applause. Great, come up here. So this is the remote. Your slides will be here. Please, the stage is yours.
Hi, good morning, everybody. So when I was a young man, my training was actually in broadcast engineering. I worked in radio and television. And my first job when I was done with university was producing a television show. And this made my mother very happy, because when her friends would ask her, "Oh, how is young David doing?" she could brag to them that he worked on a television show that they all knew. But in 1999, I switched gears, and I went to go work at ARIN, the IP address registry in North America, like the RIPE NCC here in Europe. And in that job, I was managing IPv4 addresses, IPv6 addresses, autonomous system numbers. And back in 1999, ARIN was actually responsible for administering in-adder.arpa, reverse DNS zones for IPv4, IP6.arpa, IP6.int. Okay, any one of those words, my mother didn't understand any of them. And she didn't understand them because she was born in 1945. And in 1945, the most advanced technology in her house was a radio. And over time, it became a television. And over time, it became a color television. And that was pretty cool. For a couple of decades in my mother's house, the color television was the most technologically advanced thing they owned. If you fast forward to modern times, my mother, who's now 80 or 79, walks around with an iPhone from Apple. My mother walks around with a supercomputer in her pocket. Now, my mother's fairly inquisitive. She likes to know how things work. And so from time to time, to try and understand what I do and to try and understand the world around her, she says, "David, I don't understand. How does this work? I mean, I sort of get how the telephone works, but how is it that we're able to get on Zoom and I'm able to see my granddaughter and talk in real time, and it doesn't matter where in the world you are?" Well, I've tried various explanations to help my mom understand how the internet works. And there are a bunch of different answers, but the answer that I always keep coming back to, that I find amazing, is the internet works because we're all speaking the same language. As engineers, we've adopted the same set of technical standards to ensure interoperability. And that, my friends, is a miracle. When we travel, we need to charge our devices, right? Well, when we travel, we have to bring different adapters because we've not standardized throughout the world what the shape and voltage of power adapters are. We've standardized, but we've standardized many, many times. Some of us drive our vehicles on the right-hand side of the road. Some of us drive our vehicles on the left side of the road. Why? I don't know, but we can't even standardize that. Money. Look, the system of barter has been around for eons, but over the last 50 to 100 years, currency's currency. There's only one purpose to money. You have something that you produce, I have something, I want to buy it, so I give you money. We have different currencies all throughout the world because we couldn't standardize it. And you can keep iterating through this. You can keep giving different examples, but not on the internet. Because on the internet, for the last 50, 60 years that this thing's been around, we're all using the same standards. What's kind of interesting about that is there's no rules that say we have to. If you start an ISP, You get to decide what standards you want to develop. You get to decide, well, I want to speak BGP, okay? I want DNS. I want things like email. You get to decide those. Nobody tells you you have to do it. There was an old engineering ethos for a very long time when we were building this internet. It said, my network, my rules. Nobody gets to tell me what traffic I have to accept and what traffic I can just say, no, no thank you, I'm not going to accept that. But because we want to be able to interoperate, because we want our users to be able to access the sites they want to use, because we want to access the sites we want, we choose to use the same standards. And there are two standards that we've developed that this whole internet, if you think of it as a house of cards that you build, and if you blow a little, it can fall. The internet is a house of cards built on two standards, BGP and DNS. Now, I find this interesting. First off, they're really old, okay? BGP is from the 1980s, but the BGP that we're using today, version 4, the protocol specification was published in 1995. The primary author was a gentleman named Yakov Rector with IBM. And what Yakov solved were some of the early problems of BGP that had to do with scaling. BGP didn't scale very well. Well, in 1995, he was able to solve that issue, communities, large communities, route reflectors. He was able to add some feature sets into BGP that allow it to scale. Well, it's almost 30 years later, and it's a simple question. Did BGP converge in your network? Yes? Okay, it scales. It still works. The other thing that we rely on more than anything else is the DNS. And that's kind of stupid, because the DNS is an application. Okay? The DNS wasn't supposed to be the absolute building block of the internet. It was just an application. It was a way for us to move beyond hosts.txt, and it was a way for one professor at one university to email another professor at another university about their research or about getting drinks. But we use DNS in everything. In 1983, in November of 1983, when Paul Makapetris published RFC 882, which is 40 years ago next month. I feel like it was an accident. I'm not sure. I'd really like to ask him one day, but he solved the most difficult problem in computer science, which again is scaling. The DNS is huge, right? I don't know how many I don't know how many domain names there are these days, but it's what, 500 million or something like that? It doesn't matter how many there are, because nobody has to carry 500 million domain names. Whether it's 500 million or 500 trillion, the whole thing's distributed, and you only have to care about the parts that you're authoritative for. The thing is, BGP and DNS are 30 and 40 years old, and when they were built, they weren't built with any security in mind whatsoever. The purpose was to make things work. The purpose was to interoperate. Could I route from point A to point B? Sweet, it works. BGP converged. Can I send you an email at your domain name without having to know all the hosts, the computer name and all the hosts in between me and you? Yeah, okay, great. DNS worked. But that's not true anymore. It's 2023, and the internet is involved in everything in our lives. And so security is extremely important. But we're still running these protocols at the base of the internet that are 30 and 40 years old and have no security in mind when they were designed. And that's a bit of a challenge. In BGP, we're addressing that, right? RPKI, we're trying to give assurances that routes that you're accepting actually come from the people who own those routes. We're trying to do path validation for the big ISPs and the big networks, BGP-SEC. For everybody else, there's this new technology called ASPA. We're putting security in places that it hasn't been before. We're also putting confidentiality. We're putting user privacy in places it hasn't been, right? We don't use Telnet anymore. We use SSH. We don't use FTP. We use SFTP, or better things than that. We don't use HTTP for a whole lot anymore. We use HTTPS. We're doing the same thing in the DNS, right? We can do DNS. We don't have to use UDP anymore. We do DNS over TLS. We use DNS over QUIC. The folks at Apple are trying to make the whole thing oblivious. We've added security onto DNS through this idea of DNSSEC. And the idea here is that we want to close down attack avenues by giving you assurances that when you ask for a domain's data, that the data you receive back is the same data that the domain owner intended. In DNSSEC, it relies on a chain of trust. As you go hierarchically through the DNS, you want to ensure that the keys that were used to sign the certificates that are presenting, hey, this is really me, actually authenticate. And all at the top of this entire hierarchy is the root zone. And in 2010, we were able to sign the root zone with DNSSEC keys. But the thing is, not only do you have to trust the keys, but you have to trust that the keys are kept secure. Because if the wrong people have access to those keys, then that chain of trust is broken. And so I want to talk just a little bit today about how the organization I work for, ICANN, is able to secure the keys that sign the root zone. We keep the keys, of course, the cryptographic keys, right? We keep them in an HSM, a hardware security module. Okay, lots of people use HSMs. Banks use HSMs. Lots of folks use HSMs. Our HSM is actually pretty small. It's a very small box. It's not even a 1U. It's about this big. It's tamper-proof. What do I mean by that? If you drop it, if you put it in a vehicle, if you take it where it's not supposed to be, it will fault. And when it faults, it erases its contents. It self-destructs. In order to access the key that is on this HSM, we have programmed 7 smart cards. 7 smart cards. In order to access the key, 3 of the smart cards need to be inserted into the machine. And what we did is we have entrusted 7 people around the world to be the owner of these cards. So in order to access the keys, so we want to do new signings. We want to use the key signing key to sign the zones fresh. We need 3 of those people in the same room to insert their smart cards into the HSM in order to access the key signing key. We know these people as trusted community representatives. These are people around the world who have proven themselves to be known, to be trusted, to get through background checks, and to have given us a commitment that they're willing to come a couple times a year to facilities to do these signing ceremonies. They're called key signing ceremonies. When you're a trusted community representative, what you're actually issued is a safety deposit box key, okay? And what we do is we take the HSM and we store it inside a safe. It's a very large safe. It's a very heavy safe. And there's only 2 people in the entire world who know the combination to this safe. I'm going to show you pictures in a few minutes. In a different safe, sitting next to it, are a bunch of safety deposit boxes, just like you get in a bank, okay? And the trusted community representative holds the physical key that can help open the safety deposit box. They own 1 key. ICANN owns the other key. And when you put, just like in a regular safety deposit box, you have to put both keys in, turn it at the same time, and then you can open it. The safety deposit boxes themselves are kept inside a second safe. And that second safe has a different combination than the first safe, and there are only 2 people in the world who know the combination, and it's 2 different people, okay? In between ceremonies, we keep the HSM in 1 safe, and we keep the smart cards inside the safety deposit boxes inside the other safe. Okay, that seems pretty secure, right? Well, these safes are inside of a cage. It's a steel cage. And the only way you can get in the cage is if 2 other people badge in. They use a badge, They use a long combination on the keypad, and they use an iris scan. So the only way to get to the smart cards to access the key signing key is to have two people open up a room, have two other people open up one safe, have two other people open up the other safe. Then you need the physical keys to open the safety deposit boxes that have the smart cards. Okay, we have a few levels of abstraction here of security. But that's not enough. This cage is located in a locked room. The locked room has an inner door and an outer door. To get into the inner door, once again, you need two people who have the correct eyes for the iris scan, the correct key cards, and the correct numbers sequence on the keypad. To get to the inner door, you have to get through the outer door. To get through the outer door, you just need a key. Okay, doesn't seem very safe, except the outer door is located inside of a data center. The data center is located, I promise you, in the middle of nowhere. When you land on a plane at Washington Dulles Airport in suburban Washington, D.C., you get in a car. You're not going to bicycle there. You get in a car, and you drive about 2 hours to the middle of nowhere. Then you drive an hour past that, and you find a data center that's not on a map. And when you get to the data center, the first thing you see are men and women with really large guns. Because this is America, my friends, and we have a lot of guns. I actually don't like guns, that's just me. And so it's always unnerving for me when I walk into these data centers and you get to the entrance, and it's all these men and women who are professional guards who are carrying around these guns, and on the wall is another rack with automatic guns, and it's a lot of guns. To get into the room that I showed you earlier, you have to get through a secure data center. Again, it's not on a map. And there's actually two of these. They're both in the United States for legal purposes. One of them is on the East Coast in Culpeper, Virginia. The other one is security by obscurity. It's in a place called El Segundo, California. If you've been there, you know this is Los Angeles. It's Los Angeles. It's a major world city. Many of you have been there. But here's the thing. It's an unmarked building in the middle of an industrial neighborhood by the airport in Los Angeles. Good luck finding the building. So security through obscurity. 4 times a year we get together for ceremonies where we need to use the keys, to sign the keys for the root zone. In order to have a ceremony, we need enough people there. We need the people who know the combinations to the safe. We need the people who have access to the room. And of course, we need the trusted community representatives. It's not enough just for me to stand up here and say, we have all these processes that are kind of over-engineered, but whatever. We have these engineered processes to keep things safe. We also broadcast all of these ceremonies live as they're happening, and anyone can watch them on YouTube. And I assure you, when you're sitting at your home tonight or when you're sitting in your hotel tonight, if you're having trouble sleeping, just bring up one of these key ceremonies because it makes watching paint dry exciting. We broadcast these ceremonies to ensure that there is trust in the process that we're doing. And what do I mean by that? The whole thing is heavily orchestrated. Anything you do during a key ceremony is in a script. David stands up. David walks over to a safe. David takes the safe out. I mean, you can literally read this. The ceremony administrator asks the root zone maintainer representative to identify themselves in front of the room, and it just keeps going. It's 50, 100, 150 pages. Every action is scripted, and the script is available online for you to follow along. And from time to time, cryptographic experts and DNS experts who are watching these ceremonies are able to say, hey, you guys did this at step 47, but I've got a better idea. And they can share this idea, and we can improve the ceremonies to make them safer and more secure. The process is streamed, it's recorded, external witnesses are watching every step, and then all of the materials are posted online to review afterwards. It's not just enough to operate internet infrastructure anymore. We have to do it safely. We have to do it securely. And I wanted to give you just a little bit of insight on how the keys to the root zone of the DNS are kept secure. Thank you.
David, please. Yeah, don't leave yet. Nope. Yeah, please come up. So, yeah, the first thing that struck me, I mean, this is crazy. I'm visioning those, you know, Ocean 7, Ocean 11 movies and Bond movies, just trying to break that. Now, there are a few questions I'd like to ask you. The people from the audience has asked that.
Sure.
So one of the first ones is, so what happens if some of the keys are damaged or lost? So there are 7 of them.
Yes.
So what happens if you damage one? Does the system continue to work?
Yeah, so there are 7 smart cards, and we hope that all of them don't get damaged. When one is damaged, we can simply unenroll it, enroll a new one. We try and, I was once asked, why is it 3 of 7? Why did we choose 3? There's some sort of calculus that says that is the balance between security and practicality, right? Mm-hmm. So we don't just bring 3 TCRs to a ceremony. If one of them's damaged, we can't do it. We bring 4, we bring 5, we bring 6, we bring 7. And we try and recover from these types of errors, because after all, it's just a 50-cent smart card, right?
Good. So there's another one. What are the measures to prevent the root key loss if HSM is damaged? So that makes the whole point. If somebody takes it to the vehicle, it's got damaged, it erases anything, the whole thing just loses the purpose.
Yeah, so we sign the zone in advance. The signature is good for about 18 months. But we have more than one HSM. We actually have a lot of HSMs. And we have backup keys to go along with the current operational key.
Yeah. OK. There's sort of a not nice question. What happens if somebody dies, you know, falls asleep?
No, that's an important question. OK. Dan Kaminsky, many of you know him. Dan Kaminsky was one of the key holders. It was actually one of the, we have, in addition to 7 key holders in each facility, we also have backup keys. We have backup keys in case the keys are lost or damaged as well. Dan Kaminsky was one of the shareholders of the backup keys. And Dan died very unexpectedly in his mid-40s. We had this whole engineered process where everything is accounted for. We did not account for what happens when he dies, because he lived in America at the time, and his keys were the property of his estate. And guess what ICANN couldn't do? Get his keys. We couldn't go and say to his survivors, hey, can we have this key, please? Because he didn't tell anybody. So what we've learned is that when you are a trusted community representative, when you're holding one of these keys, we've asked you to now please tell somebody. Tell somebody, your spouse, your lawyer, somebody you trust. Tell them you do this. Little primer on what it is, why you do this, and where you keep your key. Mm-hmm. If you hold one of the safety deposit box key and you die and we can't get it, okay, it's not a huge deal because all we do is we literally drill it. We'll get out a locksmith, we'll drill the thing open, and we'll replace it. But it takes a lot of time and a lot of effort.
But isn't the whole point that you need, you know, 3 of them to actually function? So if there are 7 and one is just missing, so that doesn't seem to be a problem.
It's not a problem, except we'd like to keep 7. We'd like to keep the robustness of the ceremony. Mm-hmm. So just the general thing is we're all going to die at some point. When you die, try and make it easy for the keys to be returned.
Yeah. And these big backup keys, are they secured in the same way?
Yeah, the backup keys are also kept well secure in those safes.
Okay, so what puzzled me as well is that, yes, you are filming everything, you are recording every step, you are basically making the whole process so public that if somebody really has any intention of breaking that, they have the whole menu.
They do, except you can't see the keys. Funny thing, when you're opening up safety deposit boxes, it's a physical key, right? Physical keys have teeth. You can see the shape of the teeth. So if we show the key to the camera, that allows someone to say, oh, I can capture a video still. I can recreate the key. We did that by accident. And that was a learning experience where we had to, the transparency, which is a feature, is also something we have to be careful of, because we were talking about a physical key with physical teeth. So now when I open up, I'm one of the ceremony administrators and I have one of the keys. When I put my key in, I try and hide it from the camera so you can't see what I'm doing.
Yeah, so HD cameras are kind of no-no in this situation. Yeah, I got it. So does anybody has in the audience, you know, a physical question? Do you want to raise a hand and you will be given a microphone, or you can use the Menti, the code you already had. So before I dismiss you, can you, in 1 minute give maybe an idea to us, a future for that? So what else can be done using methods like that? What kind of future, more secure, or in what ways does it actually open for us? Because one thing is, yeah, it's a nice ceremony. Other thing is when I'm configuring my domain, and so on, I don't want it to be too complicated. No, you don't want it to be too complicated, but you know what you do want complicated? When your bank is using HSMs. See, it's pretty crazy because we know how it works and we know we shouldn't be doing this, but we actually trust, many of us trust our banks to do electronic banking with us, right? I pick up my phone, I can use Face ID or I can use a passcode, and that gets me right into my bank account. And I'm trusting somehow that that's going to be secure over the internet. I actually don't trust that. I don't trust that at all. But what I do trust is my bank has good processes to give me my money back if you steal it. There are, because it's 2023, because we're doing more and more with internet, because so much, everything we care about, for the most part, is becoming online. This idea of key security, the idea of robust procedures and transparent procedures to make sure that HSMs and other ways that we store keys are kept safe become even more important for us to be able to live our lives, whether we are operating in the military and we have nuclear weapons that are available online, or whether we're just doing banks or our children's schools, right? It's all about keeping the keys to everything that we do safe and secure. Okay, thank you so much.